Assalamu alaikum warahmatullahi wabarakatuh. Welcome to the course of Electrodynamics. My name is Muhammad Salim. Here are the outlines of today's topic. We will discuss some basic concepts about waves, introduction to waves in one dimension, solution of one-dimensional wave equation, and the last one, linear superposition principle and one-dimensional standing wave. So what is wave? A wave is a traveling disturbance that moves through space and matter. Waves transfer energy from one place to another, but not matter. Types of waves in physics. Different types of waves have a different set of characteristics. Based on the orientation of particle motion and direction of energy, there are three categories: mechanical waves, electromagnetic waves, and matter waves. So coming to the first one, which is mechanical wave. Mechanical waves are waves that need a medium for propagation, such as sound waves or water waves. On the other hand, electromagnetic waves, which are also called as non-mechanical waves, which do not need a medium for their propagation, such as X-ray waves. The last one is a typical one, which are called as matter waves. This concept is a little complicated to understand. The dual nature of matter, its ability to exist both as particle and a wave, was first brought to light by the founders of field of quantum physics. For example, a beam of electrons can be diffracted just like any beam of electromagnetic radiation or water wave. This property of matter was brought forward by Louis de Broglie's hypothesis. We will discuss some more definitions which are very important for our later on topics. First one is a dispersive medium. So what is a dispersive medium? A dispersive medium is a medium in which waves of different frequencies travel at different velocities. With electromagnetic radiation such as light, radio waves, this occurs because the index of refraction of medium is frequency dependent. A medium in which speed of wave is independent of frequency of wave is called as non-dispersive medium. For example, air is a non-dispersive medium of sound waves. Longitudinal wave. A longitudinal wave is a wave in which particles of medium move in a direction parallel to the direction that the wave moves. Transverse waves. Transverse waves are also characterized by particle motion being perpendicular to wave motion. And last one is standing wave. What is standing wave? A standing wave is a wave that remains in constant position. It's called as standing wave. So, what is one-dimensional wave? A classical one-dimensional traveling wave is a quasi-coherent collective phenomenon that of disturbance associated with the localized excess of energy in a macroscopic continuous medium which propagates as time progresses. So we are discussing a classical medium here. A classical one-dimensional traveling wave is a quasi-coherent collective phenomenon. What does it mean? It means that a one-dimensional traveling wave is a wave which has same amplitude, same wavelength, same angle, same frequency and same phase. Then it is called as one-dimensional traveling wave that progresses as time progresses. So in a dissipation-less, non-dispersive medium, the shape or profile or envelope of the wave propagates with constant velocity. As we have read earlier that in non-dispersive medium does not depend upon frequency, so the velocity of the wave will be constant. Rather than in a dispersive medium, a traveling wave consisting of a linear combination of different frequencies, the various frequency component of wave will each propagate with different speed. Thus, the overall shape of the wave will change with time in a dispersive medium. So, in the case of dispersive medium, because dispersive medium depends upon the frequency, so changing the value of frequency will also change the speed of the wave. In a dissipative medium, the wave amplitude will decrease with time. Often real media are not only dissipative but also dispersive. Thus, dissipation in a medium may also be frequency dependent. Classical media can be both dispersive and dissipative, one or both or neither. A classical one-dimensional standing wave is a linear superposition of two counter-propagating traveling waves, such as a standing wave on a string instrument. Standing waves do not propagate in space, although they can do evolve in time. Let us consider a one-dimensional transverse traveling wave. For non-dissipative, non-dispersive media, the transverse shape of a traveling wave f of z of t is invariant under space translations and time translations. What does it mean? It is clear from the figure that the transverse shape of the wave does not depend upon the time. As time changes, the transverse shape does not change. It is invariant under space translations and time translations. If we want to calculate the transverse displacement from the 2 points, then it will be equal to f of z of 2 is equal to f of z minus v into t2 minus t1 of t1, which is equal to f of z minus v into t2 minus 0 at t1 is equal to 0, which is equal to f of z minus v2 t2 is equal to 0. If we want to check the displacement from f of z at t1 is equal to, which is equal to f of z minus v into t1 minus 0 of 0, which is equal to f of z minus v t1 of 0. So what does that equations means that we have calculated the displacement from these 2 points and these 2 points, which are here. In general, f of z of t for one-dimensional traveling wave at position z at and time t is equal to a special type of function g of z minus vt, the function f of z of t that mathematically describes the one-dimensional wave motion or wave propagation is not arbitrary. What does it mean? It means that the wave propagation is not arbitrary, it is in fixed direction. What does it mean? It is a very special or very casual relationship of the locations of one-dimensional wave in both space and time. For f of z of t is restricted to a casual subset of functions g of z minus vt, such that classical traveling waves obey causality. This means that the argument of casual g functions z minus vt is constant, independent of space z and time t, such that argument of z minus vt is equal to constant. The following are some examples of mathematically acceptable casual functions describing dissipationless, dispersionless classical traveling wave in one dimension. Here a and b are constants, for example, independent of frequency. A Gaussian wave, sine or cosine wave, or cusp wave. These waves shows causality. What does it mean? It means that the one-dimensional traveling wave is not arbitrary. So here are some examples of mathematically unacceptable one-dimensional wave functions. These mathematically wave functions shows arbitrary wave propagation. Now we will derive one-dimensional wave equation by an example of transverse mechanical traveling waves which show on a string which shows or which obeys Newton's second law. If a stretched string is transversely displaced from its equilibrium position as shown in the figure below, the transverse displacement of the string of its equilibrium position at a point z along the string at a given instant in time t is mathematically described by the function f of z of t. So let us analyze the forces acting on small infinitesimal segment of the string. As can be seen from the figure below, at any given instant in time t, the net transverse force del f of y of zt acting on an infinitesimal string segment of length del z between z and z plus del z on a string with tension t is. As we can see from the figure below, we have taken 2 points z and z plus del z which are very close to each other, and we want to find the net transverse force, which is equal to del f of y of zt is equal to t prime of y into z plus del z of t minus ty into zt, which is equal to t sin theta prime minus t sin theta. For small transverse displacements, string tension is equal to constant. What does it mean? It means that sin theta will approximately equal to theta, which is approximately equal to theta. If we take the small transverse displacements which are very close to each other, then sin theta and tan theta will also be equal to each other. So del f of y of zt will be equal to t tan theta prime minus t tan theta, where tan theta is called as a slope. So del f of y of zt is equal to t into partial f of zt over partial z of z plus del z, and partial f of zt over partial z of z, which is equal to t into partial square f of zt over partial z square of del z. Thus del f of y of zt is equal to t into partial square f of z of t over partial z square del z for small transverse displacements of the string from its equilibrium configuration. If the mass per unit length of the string is we take mu, which is equal to mass of the string per length, where the total mass of string mass is equal to mass of the string and the total length of the string, then according to Newton's second law, we know that del f of y of zt will be which will be equal to m a y of zt. So we are putting the values where a y of zt is equal to transverse acceleration in the y direction at the point z at time t, then a y of zt is equal to partial square f of zt over partial t square. So in the string segment of the infinitesimal length del z has mass m is equal to mu del z. So the del f y of zt will become, which is equal to m a y of zt, which is equal to mu del z of partial square f of zt over del t square. We have put the values of a y of zt, which is called as transverse acceleration and mass, but del f y of zt is approximately equal to t into partial square f of zt over partial z square del z from the transverse force imbalance relation above. For small displacements, t into partial square f of zt over partial z square del z, which is equal to mu del z partial square f of zt over partial t square, or partial square f of z of t over partial z square is equal to mu over t partial square f of zt over partial t square. Note that from dimensional analysis, t over mu have same sign, same SI units. So from conservation of energy associated with traveling waves propagating on taut or tight string, it can be shown that v is equal to t over mu under root, which is equal to longitudinal speed of propagation of transverse waves on a string. For dispersionless media, note that v is equal to constant, which is not equal to frequency. Thus we arrive at one-dimensional wave equation for transverse traveling waves propagating on a tight or taut stretch string. So we have coming to the solution. Thus we see that the wave equation is an second order linear and homogeneous differential equation. So the solution of wave equation are all functions f of z t of the form where longitudinal position z and time t are causally connected to each other by z minus vt is equal to constant, such as all the functions g of z minus vt is equal to constant. The requirement that f of z of t is equal to g of z minus vt explicitly means that u is equal to z minus vt argument, which is equal to argument of g function, such that partial f over partial z is equal to dg over du, partial u over partial z is equal to dg over du, because partial u over partial z is equal to partial z minus vt over partial z is equal to 1. And similarly partial f over partial t is equal to dg over du partial u over partial t, which is equal to minus v dg over du, because partial u over partial t is equal to partial into z minus vt over partial t is equal to minus v. So partial square f over partial z square is equal to partial over partial z into dg over du by putting the values, which is equal to d square g over du square into partial u over partial z, which is equal to d square g over du square. And partial square f over partial t square is equal to minus v into partial over partial t dg over du, which is equal to minus v into d square g over du square into partial u over partial t, which is equal to v square into d square g over du square. So by comparing that equation and the first one, we have concluded that partial square f over partial z square is equal to 1 over v square partial square f over partial t square, which is one-dimensional wave equation. Thus g of u can be any differentiable function satisfying u is equal to z minus vt. Note that since the wave equation involves the square of the longitudinal propagation speed v, then another acceptable form of solution is f of zt is equal to g into z plus vt, which will be opposite in direction. Thus there are two generic possible acceptable solutions. F of zt of t is equal to g into z minus vt, where z minus vt is equal to constant. Thus if t increases, z also increases. Whereas f of z of t is equal to g into z plus vt, where z plus vt is equal to constant. Thus if t time increases, z decreases. What does it mean? Physically this means that f of zt is equal to g into z minus vt represents a one-dimensional wave propagating in positive z direction, whereas f of zt is equal to g of z plus vt represents a one-dimensional wave propagating in the negative z direction. As we have concluded that the traveling waves can propagate in positive direction as well as in negative direction. So we have introduced the linear wave equation and the linear superposition principle, provided that the initial simplifying assumptions that the displacement from equilibrium is small, such that sin theta, theta and tan theta are equal, then the principle of linear superposition tells us that f total of z of t is equal to summation I is equal to 1 to n f phi of zt is equal to f1 of zt plus f2 of zt plus f3 of zt plus so on, is also a solution of linear wave equation. Note that in general, f of total of z of t is equal to summation I1 to n gi of z minus vt plus summation j is equal to 1 to m hi of z plus vt. What does it mean? It means that the traveling wave propagating in the positive z direction is right, and the traveling wave propagating in the negative z direction to the left. This one is going to the left, and this one is used for the traveling wave propagating in the positive z direction. Most generally, f total of z of t is equal to linear superposition of left and right moving propagating waves. So coming to our last topic, which is a called standing waves. What is standing wave? A standing wave is one which is stationary in space, is formed by superposing two identical traveling waves, except that one is left going traveling wave and other is right going. But it is saying that one is consider one is traveling in the positive right direction, and similarly the next one which is going into the negative z direction. Both waves are identical waves. This type of wave is called as standing wave. So the formula of standing wave is equal to f of total of z of t is equal to g of z minus vt plus h of z plus vt, where g of z minus vt is equal to a sin k into z minus vt, which is equal to a sin kz minus omega t, and g of z plus vt is equal to a sine k into z plus vt is equal to a sine kz plus omega t. So what are these new terms? What is a, what is k, what is omega? So we learn it from here. Definition of nomenclature used in wave propagation. A is the amplitude and v is equal to f lambda is the longitudinal speed of the propagation of wave in meter per second. F is the frequency of vibration of the wave in hertz. Time period t is the time period of the wave which is reciprocal of frequency. Lambda is the wavelength in meters. Omega is the frequency, angular frequency, which is equal to 2 pi f. Angular frequency, which is measured in radians per second or radians per second, and k is equal to 2 pi lambda. K is called as a wave number. As we know that v is equal to f lambda, we can written this as 2 pi f over 2 pi over lambda. So by putting the values, we get v is equal to omega over k. Here are it is called a, which is called amplitude, and lambda is called the wavelength between two crusts or two troughs, and time period is called as the time taken to complete one vibration is called as time period. So returning to the discussion of the standing waves as a linear superposition of left going and right going traveling wave, f total of z of t is equal to g of z minus vt at right plus h of z plus vt at left, where g of z minus vt is equal to a sine kz minus omega t and g of z plus vt is equal to a sine kz plus omega t. Then f total of z of t will be equal to a sine kz minus omega t plus a sine kz plus omega t. Now as we know that sin alpha plus beta is equal to sin alpha cos beta plus cos alpha sin beta, or sin alpha minus beta is equal to sin alpha cos beta minus cos alpha sin beta. So by putting the values, f total of z of t is equal to a into sin kz cos omega t minus cos kz sin omega t plus sin kz cos omega t plus cos kz sin omega t, which is equal to 2a sin kz cos omega t. Thus f total of z of t will be equal to a prime sin kz cos omega t, which is equal to 2a sin kz cos omega t. Here we have defined a new term which is equal to a prime. A prime is equal to 2a. It is called one-dimensional standing wave which does not propagate, move in longitudinal plus minus z direction. The question arises here, why have we studied one-dimensional standing wave? Because we want to check that either one-dimensional standing wave can propagate in positive z direction or negative z direction. So we have concluded that the one-dimensional standing waves cannot propagate in either positive or in negative direction. They are stationary waves. So the next topic will be the sinusoidal voltage, a sinusoidal one-dimensional wave equation. So that is very necessary for us to derive one-dimensional standing wave. So coming to the conclusion, what we have studied so far. First of all, we have studied waves and their types. There are main three types of the waves. Then we have brief introduction of one-dimensional wave, and we have discussed their characteristics. Then we have studied the causality of wave. Causality of waves shows that the wave propagation is not arbitrary. It is a causal function. Then we have derived one-dimensional wave equation. Later on we have find the solution of one-dimensional wave equation, and we have further derived that the one-dimensional wave equation may have two directions, either in positive direction, either in negative direction. So we have introduced superposition principle. After superposition principle, we have studied one-dimensional standing waves. They are stationary waves. They have arbitrary direction. So any questions anyone have, feel free to ask. Thank you so much. Allah Hafiz.